今天邀请到3名教授给我们做一个报告。简单的给大家介绍一下。马老师于1980年在中国科大获得这个物理学学士，3年呢，在这个加州大学物理家学位，有3年到9年。在西雅图华盛顿大学国家核物理研究所读研究生，9年到8年，在加州理工学院担任这个摩瑞理论物理研究员，98年到90年，在进入明尼苏达大学之前，在这个洛萨拉莫斯国家实验室，欧根海默研究员，08年，杨老师当选美国物理学会的会士。所以说，他在理论昨天理物理学方面做了非常重视。那么今天下午，那么我们有幸请到秦老师，大家说一下 the original and evolution of the elements。那么秦老师主要是因为可能有一个日本客人，那么秦老师可能可以用英语来做一个报告，大家特别是学生可以。听力啊，熟悉一下这个英语。那么下面就热烈欢迎啊，给大家。
Thanks everyone. Thanks Katie for a nice introduction. And this is the third time I'm visiting Fudan University, but the first time on this part of the campus. I remember that the first time I visited Fudan was exactly the time before I went to the US in 1989. And I was being trained at the Shanghai Foreign Language University. And so I was looking for my high school classmates in the university. But that's the first time. The second time I was recruiting graduate students for my university. The main campus is there most times. And but I didn't get to talk to the students in this way. And I'm very glad that it's the first time I actually gave a lecture again. So as Katie told you, we're talking about the origin and evolution of the elements and what are the most recent developments. And I'll try to speak slower so that it's easier for you to warm up to my language. And the other thing is that I'm really, how do I say, pay much attention to how this audience is following my talk. So if you ever have questions regarding what I just said, you can stop me anytime. It doesn't have to be that I have to finish all my slides. You can stop and go anytime you wish. Okay? The point of the talk is to actually understand something. It's not because I want to hear and go through my slides. That's not the purpose. Okay? So we try to understand something. The research I'm involved with, the origin and evolution of the elements, is basically in the form of the field of nuclear astrophysics. And perhaps quite a few of you know what the nuclear physics is. Quite a few of you also know what astrophysics is. But what exactly is nuclear astrophysics? It's like with neutron groups. I will try to explain a little bit what nuclear astrophysics is to start with. But before I go there, I first give you the overall outline of my talk. I will talk a lot about the stars. That's what astrophysics is talking about. How stars evolve, and during the evolution, how nuclei are made, along with the stellar evolution. And there's quite a bit of the stuff that I may not have time to get to, but I also wanted to tell you the history of how the process of making different nuclei started with the beginning of the universe. And the progress and all the way to that. So that's still a hint of evolution. But I'll have to touch upon that a little bit. Most of the time, we'll be talking about stars and how stars make it up. So I'll talk about what nuclear astrophysics is. What is nuclear astrophysics? As a physicist, when you come to graduate school or even go into a physics department, you say, what physics is about? The physics of the grandiose goal is trying to understand everything occurring in the universe. In terms of a very small set of fundamental principles, right? That's what physics is. What nuclear astrophysics is essentially trying to make the goal very concrete. Basically, we wanted to understand everything going on in the universe. Obviously, we are talking about the universe mostly in the sky. Whatever happens in the stars, in the galaxy, things like that. That's kind of universe, not the mundane world we live in here. So in the universe, what's going on in stars and galaxies, and how those phenomena and processes are connected to fundamental physics in terms of these constituents. Everybody knows that fundamental constituents of matter, can be thought about in terms of quarks and leptons. We have three generations of these particles, and they talk to each other by exchanging bosons. You have electromagnetic interaction, like the Coulomb force, right? So you get exchanging photons, and you also have very strong force by imparting to nuclei, and that through exchange of gluons. And in nucleus, we can also undergo weak interaction, and in the process, you emit an electron neutrino or anti-neutrino, and those are called the weak interaction. So those are the fundamental ways these fundamental particles talk to each other. And the goal of nuclear astrophysics is to try to somehow connect everything that happens in the universe, especially in terms of stars and galaxies, to these particles and how they talk to each other at nuclear astrophysics. Now, one thing I haven't mentioned yet, honestly, is that fundamental particles, we know that galactic matter, which is ordinary matter making up the stars, can be talked about in this way. But what about the other type of interaction, which is gravitation? On the Earth, you feel gravity every day, right? Every time you walk or you sit down, you jump, you feel gravity. So what about gravity? Now, on the scale of an elementary particle, gravity is ignored because we know that it's so weak, the gravitational constant is a very small thing. And each individual particle is very light. We don't feel that gravitation. But on the scale of astrophysical scales, like a star, or even the Earth, like planets, gravitation is very important. The reason is very simple. That is, first of all, it is a long-range force. That means no matter how far away you are, so long as you have mass, you can also feel gravitation by other means. And that is in strong contrast with the strong interaction of weak interaction. And those forces really only occur on microscopic scales, right? So when you go long scales, you can forget about it. Now you say, well, what about electromagnetic force? When you start learning about physics concepts, Coulomb force already tell you that it's the same force law as a gravitation, 1/r squared, right? So you get the long-range force as well. But the unique thing about the gravitation is the following thing. Unlike electromagnetism, you can have positive charges and negative charges. Like charges repel, unlike charges attract. But gravitation has only one kind of mass. All kinds of masses attract each other. So whereas on large scales, the charges of positive kind and negative kind, they cancel each other out. So on large scales, you only have a neutron. So even though gravitation is long-range force, we don't have the charge to let them talk to each other. So on a long-range scale, electromagnetism do not function either. Then afterwards, the last kind of fundamental interaction with the gravitation. Even though for individual particles, they talk to each other through gravity very weakly, but you can have assemblage lots of piles of these particles together. That's why we care about gravitation when we talk about astrophysics, because we are now talking about quantum stuff, right? Okay. I used to do these very simple demonstrations, but to drive home the idea why gravitation is such an important thing. I do this very simple demonstration to say, what exactly I'm doing here? I'm holding up this pointer, right? Okay, my finger is holding it up. That means there's some force sticking finger to this thing, right? And I'm also fighting against what? The Earth's gravitational pull on the same thing. You think about it, what is the force nature between my fingertips and then this pointer? It's essentially electromagnetic force. It's the residual of the gravity. There's some positive charge and negative charge distribution. But basically, it's neutral. My finger is also neutral. But the distribution is not exactly circularly symmetric. It cancels exactly out of these type of distribution. You can have polarization, right? So the residual of that electromagnetic interaction between my fingertips and this thing is fighting against the entire Earth, pulling on the same thing. That tells you how strong the electromagnetic interaction is and how weak the gravitational force is. But nevertheless, it's said that the entire Earth is still very important, right? Negative gravitation. So that's the idea. Now, this is the basic goal to understand what astrophysics is. But in Chinese, we say that new people should say it like, or people should say it. Basically, you cannot boast all the way you want. You have to show what you really have got, right? You have to show me what you have really got. Nuclear astrophysics has to slow. That's a slogan. You have to demonstrate what we have achieved. And let's see how much we have already achieved. First of all, I want to say that the standard model of particle physics is extremely powerful. It's the most beautiful theory, most complete theory we have ever come up so far. Okay? And how powerful it is that when you think about it, real science, you have to be very precise, quantitative. You cannot just say that, oh, candidly, or this is how it goes, or nothing like this. No, you have to say that what exactly is, for example, the mass of the neutron, the mass of a proton. And not only that, you have an error on top of it. Yes, this is how precise science is done. And so the theory of the standard model of particle physics is so precise. These days, we actually can really calculate the neutron and the proton mass difference. Everybody in nuclear physics know that neutron is slightly more massive than proton by about 1.293 megavolts. But each of the particles weigh about 938 megavolts. And we are able to calculate this difference as a few parts to 1,000 to that accuracy. And the error bars on this calculation is about 10%. Okay, from fundamental theory, all you need to do, remember the parts and remember the fundamental interactions. There are some fundamental constants we are not able to predict, but we can basically fit it through these measured methods. For example, this is the composite of some parts. It's mass is known, and then this mass is also known. This mass is known. You can fit all the fundamental constants like that. And then the parts of the masses for these other composite system parts are predictions. And the predictions is basically indicated by these red dots. And the line over here with the thickness is essentially the experimental measured value with error bars. So you can see that, the prediction like that, and it's perfectly in agreement with the measured masses. So that's how good we are. Right? So why that is important? It is important because the universe was created in a state where everything is at very high temperature, so everything is in thermal equilibrium. When everything is thermal equilibrium, we know that there's a Boltzmann law. Basically, saying that if something is more massive, then it's going to be fueled, right? If the neutron is slightly more massive than the proton, then when the universe starts in hot state, they're going to be fewer neutrons than protons. And so that tells you, initially the universe was proton-rich. And as the universe cools down from a high temperature, you can no longer stay at 3 neutrons or 3 protons anymore. Eventually they will combine to make a bound neutron, because that's more favorable energy state. But because it started with a proton-rich state, it tells you the limitation of this nucleosynthesis process. How much other nuclei you could have been. And that is called the Big Bang nucleosynthesis. Because you start out with a proton-rich state, most of the Big Bang nucleosynthesis gives you is just proton, hydrogen. By mass, 75% of the mass is tied up in protons or hydrogen. And the rest of the protons, along with the few neutrons we have in the beginning, is combined into the helium-4 neutron. That's essentially the story of Big Bang nucleosynthesis where the universe started. That's all you're going to get because it's a proton. And you know that in order to combine protons and other healthy nuclei together, light tries to repel. You have to overcome the Coulomb barrier moment. And you don't have the time and the good conditions to make a efficient charged particle reaction to go on in other universe that way to make heavier people. That's how you separate them. Now, then you look at our sun. You can look at how the sun is made of in two different ways. One way is that you pick up pieces of the meteorites which fell onto the Earth, because we think that the meteorites are essentially like the building blocks left over from the building up of the entire solar system. You look at the meteorites, you do your analysis in the laboratory, you measure all these abundances of these different isotopes, and that's one way to find out how the sun will be made of. The other way is you look at the surface of the sun, because whatever the sun is made of, it will be characteristically, be absorbing particular wavelength of light, and the sunlight from beneath the atmosphere of the sun goes through that atmosphere. Some of it will be absorbed, so you can detect what particular element is in the total atmosphere of the sun. And so on both of these methods, we get essentially agreement. That's how the sun was made of. It's on this chart over here. The horizontal axis is atomic number, essentially identify each particular element. Now you have the entire periodic table. Okay? And the abundance is on this vertical axis. You can see that it differs by at least 1 order of magnitude. Abundance is so vastly different. Now, specifically, when you look at the entire periodic tables, the elements in the sun, how they are roughly distributed in terms of mass, you find out that 71% of the mass of the sun is trapped in hydrogen. For helium, you get 27%. And the rest of it is beyond helium. Astronomers call them metals. In mass, they account for about 1.5%. But the variety of all of it. So that's a very interesting thing. You see something changed between the beginning of the universe in the Big Bang and the formation of the solar system, which is about 9 billion years after the Big Bang. Now, we are nuclear theorists. You think about it in the nuclear physics way, not just with these simple numbers. So what exactly is happening when I go from 75% of the protons and 25% of the helium or to these other numbers of these different nuclei? What is really happening, obviously, is you are depleting the protons, because the protons go down from 75% down to 71%. And you are increasing helium-4 by 2% also by mass, and all the other nuclei. And we know that their number is conserved. So the total number of neutron and protons is conserved, yes? But in order to make a nuclei beyond helium, you at least have to have equal numbers of neutrons and protons. And you go to helium nuclei, you're going to have more and more neutrons and protons. Correct? So all this is to say that during the 9 billion years between Big Bang and the formation of the solar system, fundamentally what is happening is you are basically converting protons into neutrons somehow. Right? Okay, that's what's happening. Now, if you say that in free form, proton cannot decay into a neutron, right? We already said neutrons are more massive than proton, you cannot do that. But inside a nucleus, obviously, a proton can decay into a neutron. That is simply a bit of plastic. All right, that's what you can do. The other way you can do is you can move this electron neutrino towards the left-hand side. So you now have an electron neutrino. If this electron neutrino is energetic enough, in principle, it can just directly talk to a free proton and turn it into a neutron. The electron neutrino, right? You can also obviously move this positron to the left-hand side, and if this positron goes to the left-hand side, and then you will end up with a electron neutrino. An electron, like electron. If the electron has enough energy, it captures the proton, it can also turn it into a neutron. And all these processes I'm indicating here, they involve neutrinos. And remember, when you never involve neutrinos, you are talking about a weak interaction. So any of the thing you wanted to achieve from a chain evolution of this composition from the Big Bang to the composition of the sun, you rely on weak interactions. Okay? So I now just demonstrate with two simple examples how fundamental physics and nuclear physics are really connected. One is the neutron proton mass difference, which specifies the initial conditions of the Big Bang nuclear synthesis, and that allows us to understand why Big Bang only can make up to helium and no further. And then the weak interaction tells us they are crucial in order to change the initial composition of the Big Bang all the way to the process. Okay, so that's the two demonstrations. Now, talking about this fundamental way is very nice, and that shows the importance of the fundamental nuclear physics. But more importantly, now you have to say how this thing is exactly done. How are you able to turn some of the protons, into the neutrons in some environment and make this nuclear synthesis? And this is essentially the environment where we going to be talking about it, because these are the stars. Most of the nuclear synthesis happens in stars. So we now have to have a good understanding how stars work. When you think about the stars, you can think about it in a very practical way. So what does star symbolize to you? If you read poems about it, people say about the star, you normally say that it is a symbol for light. Yes, it's light, it's getting brightness, bright light. The other one is symbolizes stability. The star stays that way for a long, long time, right? So the very first thing you have to think about is that how can you make a star shine for a long, long time? When you shine, you're losing energy from the surface. You shine for a long, long time, and you lose the energy for a long, long time. And you cannot stay stable, keep on losing energy. That means there must be an energy source inside the star to replenish the energy lost from the surface. So inside the star, there's going to be an energy source. You can do a very simple estimate. Looking at the sun, how much the sun is radiating wind per second, and you calculate how long the sun has been living. Like this, you figure out that just like text, on each proton in the sun, how much energy each proton has to supply in order to maintain the sun for 5 minutes long. If you get a scale, each proton inside the sun must supply about 1 megawatt energy in order to provide all the energy that has been radiated so far. 1 megawatt per nucleon, 1 megawatt per proton. That's the energy scale of the nuclear physics. So you immediately know that nuclear reactions must be taking place in the sun in order to make the sun shine for such a long time. If that is the case, we have again come down to the question: nuclei are positively charged. When you try to put them together to make a reaction to release energy by fusion, you have to overcome the Coulomb barrier. The Coulomb barrier is very high. In order to overcome it, the particles or nuclei must have enough energy. And the way you supply energy to the particles is by making them very hot. So in order to burn the nuclear fuel in the sun to power the energy loss as a form of light from the surface, the star must be burning nuclear fuels at high temperatures in the center. And how do you get the temperature? Well, it turns out that the temperature is provided mostly by a very simple consideration, by balancing the kinetic energy and the gravitational energy. So imagine that the star is pretty much stable. That means that the gravity is not crushing it, and the pressure force is not disrupting it. These two forces must be in good balance with each other. And so when you think about pressure or kinetic energy, there are two components that immediately come to your mind. One is nuclear hot. Typically, one particle has this particular temperature, that's also its typical energy, kinetic energy. And because you can imagine that the initial form of the star is not just a spherical ball like in the sun. It must be some kind of very diffuse cloud, and its gravity slowly contracts to the final form of the star. And during this contraction, not only that you can imagine the temperature is changing, but you can also imagine that the particles inside this cloud are getting close to each other. And when particles get close to each other, you actually have to worry about, again, some fundamental physics. And say the zeroth order, the significant cloud will be consisting of protons and electrons, because it's neutral. Now, electrons, everybody know that they are fermions. Fermions, that means they obey Pauli exclusion principle. When you try to make the cloud smaller and smaller, the electrons get closer and closer to each other. And then you say that, well, Pauli exclusion principle say that, no, you cannot come into my own space. Imagine a little cubicle set up by each electron. So that's my cubicle. No other electron should be coming closer to me because Pauli exclusion principle. And now, on the mechanics value, if you nail down the position of the electron, that means its momentum must be quite sizable to satisfy the uncertainty, right? So with that momentum, you immediately will be creating some kinetic energy for this electron trapped inside of the cubicle. And these two forms of energy, kinetic energy, must be balanced against the gravitational potential associated with the proton, because each proton reacts on each electron. And so you can just rearrange this equation in the form of the temperature in the center of the star and a function of the size of the star in terms of two parameters. One is how many protons inside this cloud, or the total mass of this cloud, and the typical dimension of the star, the radius of this cloud. And so as a function of this radius, the center temperature comes up to be this equation. We can plot it out, T as a function of R. We find out that at some particular radius, the temperature will reach the maximum value. And the maximum value depends on the mass of the cloud to the 4th power. So therefore, if you must reach a critical temperature before you can ignite the licensed nuclear fuel, which is the hydrogen from the Big Bang, right? Hydrogen fuel, because hydrogen has the least number of protons, the charge is the smallest, the Coulomb barrier is the smallest, so that the temperature to ignite hydrogen is the lowest. And in order to ignite the hydrogen burning, the mass of the cloud you require is about 8% of the solar mass. So for anything lighter than 8% of solar mass, you can never become a star because you are never able to ignite hydrogen burning. Okay? So that is essentially the story about the star. You have to have enough mass. Now, once you get this idea, then you get the very simple picture. Somehow a star's life is dictated by its mass. And at least you have to be 8% of a solar mass before it can be called a star. And for yes, sure.
Why is it not even after capital R reason?
This is the actually go that over here.
What if the R is the size of the
Okay. So what I'm saying here, if you treat R as a variable, so T as a function of R, you can show that it's a curve. But I'm here is the maximum temperature of the T will correspond to some R.
oh,
Right? And so the R is no longer variable anymore for the fixed point of the maximum temperature. So if you, I don't know, if you imagine what the curve looks like. So when R is very small, this 1 R squared thing will dominate. So it becomes negative. Right? And then obviously when R becomes larger, this thing drops out, this thing will become positive and then eventually will let go of R. So you can imagine that T will go from negative and very small R, shoot up, go from 0, and then reach a maximum and then go down like little R like that. And there will be peak of the T at some particular R, which you can do by, the derivatives and all that, you can figure out what is the maximum temperature.
what's the meaning of R? The R is the data between.
It's a size of the cloud. Imagine initially you have a ball of gas. The total mass is M, the size of it is R. And then it contracts or shrinks, the mass stays the same. And then in this process, At some parts, you'll reach a highest temperature. And then if you shrink further, it doesn't need to be changing. And that is the point. So that highest temperature depends on the mass of the glass.
Thank you.
Okay. Okay, very good. So now you can see it in this particular diagram as well. So the vertical axis is now same thing at a temperature. It's a different temperature. And the horizontal axis is essentially equivalent to the radius, but this is the total density, the mass over R cubed. And so if R shrinks, density increases. So go toward the right from horizontal axis, density increases, which means the R is shrinking. And as you can see that for these type of stars, the less than 8% of the solar mass, initially the temperature increases as it shrinks, they go to the next one, and then the temperature decreases as you shrink further. And likewise for all these other cases, suppose you have more solar mass, but less than 10 of solar mass, you'll reach a temperature high enough to ignite a hydrogen burning. But the temperature you burn is not going to be high enough to burn helium. The helium is what's produced by hydrogen burning. In order to burn helium burning, you have to be at least half a solar mass or more, and you're like 7 solar masses. And so this picture, this technology, in order to process nuclear fuels, because you do hydrogen burning, then you produce helium out of that. And next thing you have to burn helium. When you burn helium, you have to raise the temperature further. And the helium burning ends up with carbon dioxide. In order to burn carbon dioxide, you have to raise the temperature further. Eventually, this kind of way of releasing nuclear energy by burning, you can go all the way to produce iron fluid. By that point, we know that iron fluid is the most highly bound nuclei, and you can possibly, fuse the iron together in the sphere of energy, right? That's the end of the nuclear burning. And not only start and reach those high temperatures to burn silicon and things like that, including iron. And for those kind of stars, at least you have to have more than approximately 10 solar masses. If you are more than 10 solar masses, we call them active stars. You are able to burn hydrogen, and after you finish that, you shrink, and raise the temperature further, and you burn helium, and you shrink further, and you keep on doing that. You can go all the way to iron. Okay, so that is the differences between stars' fate depending on their mass. If you are less than about 10 solar mass or so, you mostly will end up only with carbon dioxide in the center, and you're done. If you're more than 10 solar masses or so, you can go all the way to make iron nuclide in the center. Because the mass is not to keep on raising the temperature, to ignite all the possible nuclear burn. Okay? So that's essentially the diagram telling the fate of all these different stars. It's just to recap what I said in this pictorial way. So imagine that initially you have a gas cloud dependent on its mass and the initial size, and as it shrinks, eventually it will reach some temperature, and if you reach a temperature for burning hydrogen, then it becomes a star. And like our sun, typically 1 solar mass by definition, and the sun will be able to burn hydrogen helium, and after hydrogen in the center is exhausted, it will shrink a little bit further, and then raise the temperature to burn helium with carbon dioxide, and after that, star like our sun finishes all the nuclear burning, because no matter how you contract, it cannot burn carbon dioxide anymore. At that point, a very interesting instability can happen in the star, and what happens is that all these unstable processes will disrupt the rest of the star, the envelope, and it dispel it in terms of something called the planetary turbulence. And then what you have produced in the center, mostly of carbon dioxide by nuclear burning, by that time it's very hot, right? And so when it's hot, there's both in Chinese and English called white hot. And that's called white. So the center is called white, okay? And it's also called a dwarf, white dwarf. Because in order to reach that temperature, you keep on shrinking. When you shrink, you become smaller. And so by the end of this process, you have learned everything you possibly can do in the center of the star and the sun. You reach the point of the layer of nuclear burning, you only get carbon dioxide, and but you have become very hot in order to do so, and you also have green to a small size, and this core now can be exposed when you smell the rest of the envelope, and because it's hot, because it's small, it's called a white gas. Now, if you are born with much heavier mass, let's say 10 times more than the sun, the story is very different. Such a massive star will go through all the chain sequences of these burning until you have iron in the core. By that point, as I say, nuclear resources have been used up, and by that time, you actually have many ways of losing it, as we'll talk about. When you lose energy, you lose pressure supporting in the core, you can no longer support the core against its own gravity. The core will collapse. And hopefully then you will end up with an explosive situation called a supernova. This kind of supernova called a core collapse supernova. And this core collapse supernova end up with two kind of situations. You either leave behind a stable neutron star, or basically you collapse into a black hole. And the rest of the envelope is expelled by the explosion. And these are the two different effects of these two different types of stars. Average small stars and large massive stars. They give you very different end results, and the nucleus accompanying their life is also very different. The other thing I want to say here is that the time scale for how you can do this is very different. Small stars, even though they are able to burn nuclear fuels, but the central temperature inside the star is relatively still small. In the high mass stars, the temperature you can reach is much higher too. And nuclear reaction rates are extremely sensitive to temperature because you have to go through this Coulomb barrier quantum mechanical penalty, right? The probability is very sensitive to the energy. So for massive stars, you go through the sequence of nuclear burning at a much faster rate. And a typical lifetime for a 10 solar mass star is about 4 to 10 million years or so. Whereas the typical stars, a bit more massive than our sun, twice as heavy as our sun, so it can burn nuclear slightly faster. It takes about 2 billion years, a few billion years. So it's a very different time scale. If you think about it, after the Big Bang, you only have hydrogen and helium. You are adding anything further onto it, you have to do it inside the stars. The first stars which will be able to add new elements to that Big Bang material can be the massive stars. Because it only take about 10 million years or so before they start to contribute towards the universe. Whereas if you have to wait about a few billion years before these low mass stars start to contribute their own stars. That's the difference. Yeah.
How was the time to view first one right?
You mean this way. Okay, very good. So the question is very good in the sense that I'm talking about it in a very simplistic way, but actually the slide that extended the object. The temperature obviously decreases from the center to the surface. So if you focus on the center, then the center temperature always rises, because initially you just only burn hydrogen, and the Coulomb barrier is not that as high, and so the temperature for that inside is about 10 million degrees. About basically kilowatts, 1 kilowatt temperature. That's it. But then afterwards, you put the hydrogen and helium. Helium now the charge is by factor 2. And when you put the helium, you actually need a much higher temperature. You need 100 million degrees. And they increase by factor 10. So along that thing in the center, the temperature always increases. And so, but obviously, when you have 100 million degrees in the center of the star, slightly outside, the temperature is not going to be 100 million degrees. It's going to be like a region you can find out several 10 million degrees. So the center can be burning helium into carbon dioxide, but on the outside, you could burn hydrogen into helium. Now you see that it's a very interesting situation. So for very massive stars, you can have multiple places happening with nuclear burning. And that's the reason why the composition structure of the star is going to be very interesting. Right? It's not going to be uniform throughout. Now, I've given you the story of the individual stars, but like people, stars like to make friends. And you have a sociology of stars. Most stars actually belong to binaries. So when you have binaries, then you can have very interesting phenomena independent of this, I should be independent of it, just as an aftermath of all this stellar evolution. For example, if you have made a white dwarf because some low mass star have evolved to that point, and this white dwarf happens to have a companion, right? Then this white dwarf can further grab mass by gravitation from the other companion, and when it's increasing enough mass, it's pushed over a limit, it triggers a thermonuclear reaction. Basically, because it's still threshold fuels, you just have carbon oxygen. And when you just trigger that thermonuclear burning, and all that carbon oxygen is burning in the iron group, and in that process, you would be going through some kind of explosion, which is called hypervolation. Hypervolation equivalent because of white dwarf inside a binary, grabbing mass from the companion and burning carbon oxygen in the iron group. Likewise, we can imagine that you can have two massive stars initially in the binary. And after each of the massive stars blow up at supernova, you find the neutron of black hole. Let's say that the supernova explosion didn't disrupt this binary, basically it's still intact. Then you can imagine you have these three different kinds of binary systems consisting of the neutron star and black holes. You have two black holes going around each other. That's not very interesting for our nuclear synthesis because black holes don't really impact anything, right? But you do have gravitational waves coming from the sun systems, which have already been detected by the times. And then you can have a neutron star dancing around each other. Now, that is a very interesting thing about nuclear synthesis, and I'll talk about. You can also have a black hole and neutron star dancing around each other. All these cases will be very interesting contributions towards nuclear synthesis, and I'll talk about that. But that's the only of these stars. And I said that if you have two low mass stars in the binary, one of them is slightly more massive, so they evolve to white dwarfs first. And after it evolves to white dwarf, the other star's mass gets dragged onto the white dwarf because of gravitation. And when white dwarf's mass exceeds some limit, the fresh fuels of carbon oxygen that white dwarf gets rid of. You have a thermonuclear runaway, you have a type 1 supernova. Okay? And that's one way of making a type 1 supernova. The other way to do it is that suppose both of the low mass stars have evolved to the point of the white dwarf. You have two white dwarfs dancing around each other. And when they dance around each other, what's going to happen is they're going to radiate gravitational waves. When you radiate gravitational waves, the orbital energy is decaying. It's losing orbital energy. That means that the orbit is going to shrink closer and closer to each other. And in the end, the two white dwarfs will merge. When they merge, and say they go above some mass limits, you're going to burn carbon oxygen again into the iron group nuclei, and that's how you can make a type 1 supernova in the other. But in either case, you must have a white dwarf. And you know that the white dwarf comes from the evolution of the low mass stars, and they at least have to wait 1 billion years before that can happen, right? Now, to say that you could have these neutron star binaries and neutron star black hole binaries, etc. And what happens in the white dwarf case can happen in the neutron star binary as well. You dance around each other and you move energy by radiating gravitational waves even faster. And eventually, when the two neutrons are merged together, a chunk of very neutron nuclei can get thrown out. And those very neutron nuclei are very good for us to make heavy nuclei. Because you know that neutrons are neutral. It's a lot easier to stick neutrons together to make a heavy nuclei compared when you stick charged particles together, because then you have to overcome the barrier. With neutrons, you don't have to worry about it. Right? So when you have a neutron star merger, you suddenly have a great way of making very heavy nuclei. And even when you take into account that the two neutron stars have to lose its orbital energy through gravitational wave radiation, that time scale still is going to be much, much less than 1 gigalier. So typically, over 800 million years or so, after you made it into neutron stars, you would have merged because of the radiating gravitational waves, and you would be able to contribute into the very heavy nuclei by whatever degrees you can throw out in this merging process. And so, you can think about it right after the Big Bang. First of all, you have these very massive stars. They're going to cook up water, let's say, all the way to iron. And in the explosion, they're going to throw out these things. But if you have neutron stars, if you have two massive stars to start with, leaving two neutron stars, after they have danced around each other for a long time, and radiating away the orbital energy through gravitational waves, the two neutron stars merge. After a few hundred million years, you're going to get very, very easy. And then you wait for a few billion years, the low mass stars are going to start to contribute. And if you have two low mass stars in binary, making white dwarfs, etc., they can go either this way or that way. With that one is supernova. When they blow up, they're going to get a load of light. Right? So that's essentially the zero order story about how the universe is enriched in various kinds of environments. So let me try to summarize what I have told you so far in this more complicated part. This is another way of looking at the solar abundances. Again, the vertical axis is just telling you the relative abundances of the different nuclei. What's the horizontal axis here is in the larger atomic number. It's not the elemental thing anymore. It's actually individual isotopes. So they are the mass numbers. Again, counting the total number of neutrons and protons. We look at this balance curve. It's the real fundamental data collection we have regarding what has gone on before the solar system formed. First of all, we see that the hydrogen and helium, these two nuclei, are the most abundant. That's very simple because the areas are formed after the Big Bang. What happens essentially increase with Big Bang and debris stuff, right? So that's essentially what they have inherited from Big Bang bonds. Okay? Now you can also see that the carbon abundance is also relatively high. The carbon is also very important for any life form of organisms on the Earth, right? Any kind of organic stuff that has to have carbon. And that thing is very abundant. That's because when you form stars, you tend to form many, many low mass stars. Even though they take a long time to evolve, but eventually they will, become a white dwarf and eject whatever they have made before they come to that point. And those stuff contains the carbon dioxide they have made along the way. And so you can have lots of contribution from low mass stars to all the solar system form, and you have ended up with lots of carbon in the solar system. Okay. And I want to point out this particular peak that again indicated multiple abundances called iron nuclei. There's a nuclear physics technology. Iron nuclei are mostly kind of bound. So you try to do burning, you always try to make the nuclei toward the most stable form. And this is how the nuclear burning happens. Either in type 1 supernova I told about, or in the cold collapse supernova, I will talk about it later, that you make a lot of iron nuclei because that's the end point for fusion reactions more or less. Okay. So that's that. Now, the most interesting thing is that after the iron group, you see that the abundance decreases greatly. But even with this decreasing abundance, you still see structure. What I'm showing you here is two sets of peaks over here. I call them red and blue for easy recognition. So you see that the blue colored peaks, there are two of them, and I identify with the mass number, 138 and 208. And the red ones are at the smaller mass, 130 and 195. When you look in detail, what's in this blue peak, you find out that all the nuclei in this peak have very specific neutron number, n equal 82. Likewise, when the blue peak are at mass number 208, these guys have neutron numbers 126. And if you again take it in elementary nuclear physics, you understand that these numbers 82 and 126 are special. They're automatic numbers. And it's actually the same thing as like in atomic counterpart, atomic physics tells you there are elements like the noble gas, which are extremely inert. They do not like to take part in chemical reactions. That's because the number of electrons outside the nucleus in these noble gas elements are exactly filled complete shells, right? That's why they don't like to react, because the complete shells, in order to make a reaction, you have to get across to a different shell that costs a lot of energy. They don't do that. because energy is very costly. Likewise, a nuclei, if you have already a fixed number of shells, a closed shell of neutrons, like 82 of them or 126 of them, you try to stick another neutron or get rid of that neutron out of the shell, it's very hard. And therefore, these nuclei need to be very stable. That's why they're abundantly made. Now, that is one kind of set of peaks. But the other set of peaks is pretty strange. One is that they have lower mass numbers. And the other one is that you look at the specific numbers of neutron protons, they have nothing to do with mass numbers. Somehow we have to understand how that comes about, right? So these are the things we need to understand next. Before I go to there, I just want to show you that the nuclear burning actually really happens in stars, and the nuclei actually make the kind of tiny moving nuclei as I played. That's the end point of the nuclear burning. It is actually demonstrated by these light curves from supernova. Type 1a has one set of light curves similar. I don't want to go into there, but I want to mention a more recent supernova, which happened in 1987. Okay, the light curve is just to say that we are to display of the supernova. How does it change? The luminosity of it and the brightness of the supernova change in function of time. The vertical axis is the logarithm thing, the logarithm of the luminosity, and the horizontal axis is time in a linear scale. And what you can see here, the initial phase over here refers to the few thousand days or so, several years. This part of the curve, this is the logarithm, this is the linear, it's a log linear curve, meaning that the luminosity can be exponentially decaying, right? And when you take a log, it becomes a straight line. And you find out that the decay lifetime scale, the scale of this decay, is exactly the lifetime of cobalt 56. So when you have iron dominant nucleus is iron 56. When you make it, you don't really directly make iron 56. You have to first make nickel 56. Because the material you have to make this thing is essentially have equal number of neutrons and protons. And nickel 56 have equal number of neutrons and protons. But nickel 56 is unstable. When it beta decays, eventually it goes through cobalt 56, which has a lifetime of several months. And then when this decays, part of the time it decays into an excited state. It emits a gamma. And that gamma ray cannot get out of the debris of the supernova yet because the debris is too thick. It absorbs all that gamma. So the debris heats up. When it heats up, it radiates. That's what you see at the luminosity as the optical display. And because it's this decay powering this optical display, so brightness at function of time should follow the decay of the cobalt 56. And not only so, you also see the decay gamma ray as a signature, because these are monoenergetic gamma rays. Some of these gamma did escape to a hole in this explosion. And the satellites operating then have detected these gamma rays from the same supernova. Do we know for sure? Indeed, when the supernova occurs, it made 5 bits for this case about 7% of solar mass of cobalt 56, even though it will become high. We know iron indeed related to. Okay. Now I want to explain this process where you make these peaks, the balloon residues. That has something to do with neutron and neutron capture. And I say that neutron capture is very efficient in making very heavy nuclei because it does not have a charge. You just eat it all the way you want. Now, we can imagine that doing this neutron capture process essentially is like a playing chess. Okay? The chessboard essentially is like your nuclear charge. The vertical axis on the board is essentially the proton number, and the horizontal axis is your neutron number. And the different reactions is like the chess moves you can make on this chessboard. If you capture neutrons, you move one step horizontally towards the right. And if you become unstable because you capture too many neutrons, you're going to beta decay. When you beta decay, you diagonally go upward. Yes? And that's essentially how this chess move can be played out. And you can imagine that this will fully depend on how much neutrons are available in the environment. If you don't have any neutrons, so you can basically start with some stable nucleus, like let's say iron 56, You capture the neutron, until you move far away from stability line. By the way, these dot line is a stable line, right? When you move away from the stability line enough to the right, you become unstable. And because the neutrons are very few, before you're going to capture another neutron, you will already have beta decay. And you go back to stability. And so the slow neutron capture process, and I will describe it to you now, will always operate very close to the stability line. And that's called the S process. S stands for slow. And because you're going to always encounter these magic neutrons surrounding your captured neutrons, the S process is always going to end up building up a peak around these magic neutron numbers, because you're directly going around the stability line. And if you make up already 82 neutrons, very hard for you to accept another neutron. So they are hard to be destroyed. And if you have not be captured into 82 yet, you have 81 neutrons, it's very likely for you to absorb another neutron to become 82. So in this case, there are more things coming in, not many things going out. We pile up the nuclei at this magnetic neutron number 82. And for example, you will encounter a stable nucleus at magnetic number 82 with proton number 56, that will be barium. The element barium is in that peak created by this process. And if you add it up, 56, 82, that's 138. That's how 138 becomes peak. Okay? The same thing happens at the next magnetic neutron number, which is 126. You encounter magnetic number 126, for example, at the magnetic number 82, at 1 for the proton, and 82 plus 126 at 208, that's lag. So these are the peaks made by the slow neutron. Okay, so we understand the blue peaks now. The red peaks must come from a very different kind of thing, because we know that they are at different position of the mass. They also have no magnetic neutron numbers anymore, right? So we could basically think about, maybe we have to do the extreme case. We talk about how neutrons are not readily available. Maybe we can imagine another extreme scenario where neutrons are so abundant, you will be able to capture a lot of neutrons as many as you wish. And before you have time to beta decay. That means you will be mostly operating far away from stability in a very neutron-rich region. Okay? And if you're able to do that, the quality of the neutron capture, you're still going to be encountering a magic neutron number sooner or later. But because you're doing it in a neutron region, to encounter the same number 82, of magic neutron numbers, you're going to encounter the way you are having fewer because we're in a neutron region. For example, if you encounter 82 with the proton number 48, you add them up, 48 and 82, that's 130. So that's the 130 peak you're going to pile up in a neutron region when you do this neutron capture process. And because you capture neutron so fast, that's called a rapid neutron capture process. That's called R process. R stands for rapid. And now, after you have gobbled up all the neutrons, you cannot do anything but beta decay. And when you beta decay, initially you have magic neutron numbers when you are unstable, but after you beta decay towards stability, you no longer have the magic neutrons number. But you still maintain the information of the original maximum. And that's how we can explain the red peaks at maximum 139. The same thing. All right. So now that essentially is the explanation of the two set of peaks and how neutron capture can do these magic neutron related process. And so, just like I want to tell you, this is not just a theory, this is the real evidence to show that these things actually happen in stars. And for the slow neutron capture process, we know very well it happens in low mass stars, because the low mass stars don't have many ways of making neutrons. So the neutrons available are very few. The way we can see that they happen in these low mass stars is because on the surface of some of these low mass stars, we have found by spectroscopic evidence a very unstable nucleus called technetium. Technetium, if you look in the periodic table, it has no stable isotopes whatsoever. The longest lived isotope of technetium have lifetimes of 4 times 10 to the 6 years, 4 million years Okay, they're all unstable. So you could not have given the star technetium when it was born. Because in order to evolve to the state that the star is observed with technetium, the star would have been already close to 1 million years old. With an element with the lifetime of the 4 times 10 to 6 years, you couldn't have a supply level. But if you see the spectrum showing up technetium lines, that means technetium must be made within the last 3 million years or so the star line. And that tells us that this process, making technetium by solution, happened right into the star at that point. And so what kind of stars like that? I just told you that low mass stars, you have made a carbon oxide in the core, but because the temperature decreases from the center, although nothing happens in the core anymore, the temperature is still high enough for you to burn helium into carbon oxygen in the shell next to it. And for the out, the temperature is high enough for you to burn hydrogen into helium in that place. And this particular structure is extremely unstable. And the convective by that time, and the envelope at the time is very convective anyway, it's turning around, just like boiling water at that point. And in this process, you can imagine mixing going to happen. Just in the helium shell, where you're burning helium into carbon oxygen, some of the hydrogen from the hydrogen shell will mix into it, and the proton, basically hydrogen, going to capture onto the carbon made by helium burning. You can turn into carbon-13, and carbon-13 talks to the helium-4, and you can eject the neutron this way. That's how the neutron is available in this low mass setting. And so the basic process is like that. Helium shell, as I said, 3 helium nuclei combined together make carbon-12. The protons from the hydrogen shell gets mixed in, captured on the carbon-12 makes nitrogen-13. Nitrogen-13 is unstable. The proton inside the nitrogen-13 decays, it becomes carbon-13. And the carbon-13 captures helium-4, giving you oxygen-16 and a neutron. And if the star already inherits some of the ion from its birth material, and it captures the neutrons to make the solution compatible process, and that's the way we see the technetium on surface, because it's going to be brought up by this turbulent motion, just like boiling water. Okay, so that's how we know this process happens in these low mass stars in this particular way. And I want to say very quickly that the massive star do this thing very differently. And in order to make the rapid interactive process, the process, you cannot rely on low mass stars. We have to rely on the massive stars. And remember, I mentioned earlier that through all the process of nuclear burning, the massive stars have developed this very interesting transition shells. Inside the center, you get iron loop. But because there are other nuclear burning happening outside it, you can only process the material to silicon at that time. Further out, you only get oxygen, further out, you only get carbon, further out, you only get helium, and the furthest out, you still have the initial material of the star, which is located as hydrogen radiators. Now, when the star collapses, during the so-called supernova phase, it basically made the initial iron core into a neutron star. And the neutron star is called a neutron star because essentially it's just like a giant nucleus. The collapse under gravity is arrested because the gravitation is countered by the strong force. Everybody knows that the strong force is repulsive at short distance. When you try to collapse the entire initial core to a very small distance, essentially each nucleus is touching each other, so the entire core becomes a giant nucleus. The strong force kicks in and stops the collapse. And when this collapse is stopped, it bounces back in a large shockwave, which goes out, trying to make an explosion outside the core. And at the time, this neutron star has shrunk to this very small radius of 10 kilometers from the original core size, basically almost the size of the Earth. And the mass of the core has been changed. And you see that, keep the same mass, but you shrink the radius by a factor of several hundred. That means you have sunken very deep into the gravitational potential. your gravitational potential energy now becomes very negative. But energy is conserved. How can it become so negative in energy? Then something must be taken away from this place, right? Now, when you have collapsed the material to nuclear density, then if the place is extremely dense, it also is very hot, and any kind of fundamental reactions and interactions can think about, the star interaction, the electromagnetic interaction, there must be tight balance. The forward reactions, the backward reaction must be in equilibrium. When process in equilibrium, you can't possibly dissipate energy. You cannot get rid of energy. We can only rely on unequilibrium reactions to get rid of energy. That means you have to rely on the most weak interaction available to you. That is the weak interaction. When you do weak interaction, you involve neutrinos. It turns out that all that energy you have to get rid of in order to become a neutron star is released in all three flavors of neutrinos: electron neutrino, mu neutrino, tau neutrino, and the antiparticles. And so this is essentially telling us the supernova of this time is really dominated by neutrinos, dominated by weak interactions. Now, suppose the electromagnetic neutrinos you're going to get from this process is more energetic than the electron neutrino. Once they get out of the neutron star, they will be turning the protons into neutrons by these weak interactions. At the same time, the electron neutrino will be doing the other way around. You capture the neutron, destroy it, and turn it into a proton. Suppose the electromagnetic neutrinos are more energetic than the electron neutrinos, then this particle will be neutron. And as this material just flows away from the neutron star, and it'll cool down. And neutron proton now can combine with the helium-4, and because you have more neutrons, and helium-4 have equal number of neutrons and protons, when all the protons get locked up in helium-4, you still have neutrons left over. And then you go through some three-body reactions. For example, two helium-4 nucleus and a neutron can make a beryllium-9 nucleus. And a beryllium-9 capture helium-4, which is the alpha particle, and it becomes carbon-12 and a neutron. In this way, then you build up some seed nuclei, and you still have neutrons left over, so you can do rapid neutron capture in this process. And this is how we think about neutron capture. I think some of it is happening in this environment, right above the neutron star, where you have emitting lots of neutrinos, and the neutrinos turn the material into neutron. So just to show you the last thing, I think, to give you the real kind of a rapid neutron capture process, you make all kinds of nuclei to the heaviest kind, let's say uranium, thorium, and gold, and things like that, with mass number close to 200 and beyond. You really need lots of neutrons. And that's the place which I talked about earlier, when two neutrons are merged together. A piece of the neutron-rich matter will fly out. And when you actually have this neutron material expands, what's happening is exactly what I sort of like indicated over on this diagram. And again, these are the stable nuclei. What I initially showed is I can lay here. So initially, you already have made these kind of initial seed nuclei, as this neutron-rich matter is decaying and heating up. This is the initial nuclei we have, maximum around 100 or so. And as you go further, you still have lots of neutrons, and the neutrons will be captured out of the inside. You see the shape of the nuclei changing, and it's not to march up to heavier and heavier nuclei, and then you actually produce lots of nuclei which are in the fission. You see the just fission that goes over here, and all the other validity can also go back to the stability, and eventually you can place all the way beyond that maximum 100, all the way to 200. The two peaks here seem to fall, 130, 105 is ridiculous. So I think I should stop here. I basically have talked that long enough, and let me see that I can do a summary talk here, summary slide, and show you. So what I've told you is that the universe operates such like a computer program. So you start out with some clouds somewhere in the universe, it collapses and forms stars. Depending on the stars you're going to form, the low mass stars, when all things are carbon oxygen, and leave behind the firewall, and if you have the animal, all of you made it into the parallel cloud again, and if you become a massive star, you can all burning, make iron in the core, and you collapse at a supernova, and you leave behind you the neutron star black hole. And whatever you have exploded, you basically can return all that to the parent world one more time. And after a while, these gas going to gather again, form a new generation of stars, which are now obviously enriched in whatever these other stars have already given you. And so you essentially are doing a loop over and over again until 9 million years after the Big Bang, we form a solar system. And we now know that when each star formed, we always form along with the star many planets. And for the solar system, we had at least 8 of them. One of them is the Earth, which we stand on today. And so, after the Earth has come into being, maybe a few billion years afterwards, it goes down, organic forms start to develop, our ancestors start to crawl on the Earth. Today, we are here in this room talking about how all this can happen. All right, thank you.
精彩的报告。那么下面就是提问了，大家有什么问题都可以随便问啊，无论是中文的还是英语，都还有意思。现场大家先问，当然是网上的大家也可以问啊，就是咱们这个状啊，对啊，这样很好那个。就是看那个abundance，每次看那个，我是有一个疑问，就是 solar abundance elements 这一块因为我们太阳系应该和其他的一些星系没有什么特别大的差别，所以说那个星系那个 abundance 分布是不是就意味着这个宇宙中的 cosmetic 这个 abundance， 这个特别有疑问，因为宇宙中我们原来上不可能很精确的测量，但是我怎么来解释当前宇宙中这个 elements abundance 这个问题？
That's a good question. As I said, remember, there are time scales. When you start, you think about it, this abundance distribution and function of time. This is just we are sampling the abundance of one particular place where the sun was born. And at the time when the sun was born, it's a snapshot, right? At a very particular place. Now, the universe started with Big Bang. And there is uniform. Everywhere you have the same abundance of hydrogen and helium, 75% by mass for hydrogen, 25% mass by helium. And there's a little bit of deuterium, a little bit of lithium. That's everywhere the baryon mass is being gone with that abundance ratio, the start of it, okay? That's everywhere the same. That at least the current cosmology tells us, okay? Then what's going to happen is that what provided things beyond the helium, right? You rely on stars. Takes time. I said that first of all, you have to worry about the massive stars, because they evolve first, right? And when they evolve, they eventually become this like supernova. On the way, remember they make all the shells, remember the shell structure of the I think some of the supernova make these ions. Cool, they'll be sewn up, right? And you could also have all this silicon, oxygen, carbon, helium, things like that, when the shock absorbs through, it gets reprocessed, and some of it can be throughout that also. All of the elements, because of that particular supernova, now be added to its neighborhood. Right? So now you form a new star from the debris of that supernova. In addition to the helium and the hydrogen from the Big Bang, you're going to add up whatever the supernova has spit out for that particular place. All right? Now, in a different part of the universe, a different supernova had happened.
Yeah.
It may make the same variety of these things, but it may make different portions.
So the ratio of something abundance
It will be different. So different stars will be different. I actually have figures to show you which tell why the stars will be very different. The sun obviously is only one sampling point, it's just one data, right? So at the place the sun formed, 9 billion years after the Big Bang, that's abundance distribution you see. I'll go to the thing over here. Okay. So I am showing you 200 stars with very different composition ratio. There's a ratio for strontium to iron, there's a barium to iron, and you can see that they do have some kind of trend, which Arnold can explain, except that each individual stars are different, right? And you can see that they can differ by a factor of 10 or more in either, right? Likewise, European barium, that is actually more interesting because they are all relatively constant. I mean, these are errors, okay, these are errors, but nonetheless, the ratios are really constant. But this is very different. Strontium of iron is very different. Barium of iron is very different. And the European barium, they're both made by our process. So if you have a dominant source always made the thing this way, you can understand it. You may be adding European barium in equal proportion every time you make it. So when you go early on, the absolute balance is smaller, but the ratio is going to be changed, right? But these are different. Strontium is made by the R process, let's say. Iron is made in a different way. And you can imagine that the contributors for the iron and contributors for strontium, they have to be mixed up. And depending on how many sources they have contributed to each of them at a particular place, then they're going to be different. Right? So this is essentially the real thing. That's part of the chemical evolution. I sort of skipped over, but it really tells you that in order to map out the entire history, you essentially have to do this loop. The universe is a loop, basically, but that particular place you're going to do the looping is going to have a different detail of the loop, right? How many stars have gone through in that place, of the low mass time, the high mass time, how many neutron star mergers you have experienced. Then in the end, this is how you get to the final set. In the sun, this is how the influence can be like. But it's for different places, for example, if you form them much earlier, you're going to have a very different effect.
Thank you.
But I always say that as time goes on, the difference will wash out. Because so long as you have a finite number of sources, you keep on mixing, in the end you will have a universal thing. But we haven't reached that stage yet.
Okay.
Right?
你想关于我可能在9个领域，一个是关于这个 Qian 用生物实验上有 lithium 当然是现在。
Yeah. So lithium is a very, very tough problem in terms of observation and theory, right? Okay. So I would say that if you believe in the current cosmology, the prediction from Big Bang synthesis, then that's very solid because it's sort of like not calibrated. You could measure the deuterium abundance at high redshift. And you can also actually now measure the baryonic content using the cosmic microwave diagram. So all the kind of parameters essentially fixed for you, and you will select out a particular value for lithium. And that value is basically too high compared with the typical observed one in a group of stars. But what happens more recently is that people thought, have a lower and lower metal abundance for the stars. That means that these stars were formed earlier, closer to the Big Bang. You should see somehow this lithium, somehow match up with the Big Bang better, right? But what happens? It turns out that it's no longer even a well-defined constant plateau. Uniformly below this Big Bang value. That's what was the earlier observation. That is called a steep plateau. About a factor 3 to 5 lower than Big Bang prediction. People thought, okay, there's got to be some systematic thing, either one with Big Bang or one with the observation down, right? And what happens is that as you push towards the lower metallicity or closer to the Big Bang, the whole thing doesn't have a plateau anymore. It displays some kind of a big scatter. So now we know that it cannot be some Big Bang theory if we believe the homogeneous Big Bang. The next thing that has to be that the observation trustworthy, if you see the scatter, the balance of the stellar process. So somehow lithium is extremely easily destroyed. Lithium plus proton burns at a million resource. And so long as you are able to mix some of the lithium back down to temperatures above a million degrees or so, you would really destroy it. And this mixing process is uncontrollably or unpredictable. Actually, uncontrollable. So the star knows how to do it. It's just that we do not have a way to predict how it's going to go. The thing that we know that it's going to be spread. Now, the spread is understood in terms of this stellar process. Basically, they are destroying lithium in various ways. And so, most people, actually, most people, the kind of consensus tend to form now is that the lithium problem is no longer a theoretical problem in terms of Big Bang nuclear synthesis. It is more a theoretical problem to understand how it started to destroy lithium in this real world.
Yeah, I would like the standard uses carbon forming from carbon gel.
Yeah.
So you have involves
It's the same thing. It's really the same thing. Yeah, I should have basically go over there to talk about. So I'll show this one here. So this is a simplification. We know that three body reactions are very rare because you have to have the three alpha nuclei to meet together, right? So really, they have actually proceeded in two stages. So what you first have is the 2 helium 4 nucleus, make a beryllium 8. The beryllium 8 is disintegrated on the order of 10 to the minus 15 seconds or something like that. See that it's extremely fast, right? But nevertheless, that lifetime is long enough compared with typically how 2 alpha nucleus happen. And so therefore, it's easier for you first to form this very short-lived beryllium 8, and then have another alpha particle nearby to react on it. But in order to make this thing, because the equilibrium abundance of beryllium 8 is going to be very small because it's keep on being disrupted very quickly, right? So the small abundance of beryllium 8 has to be compensated with a larger cross-section for it to react with the alpha particle. And as that reaction is resonance, and then you require the matching of the spin parity in the control. And that's how you have to look for a resonance state in control to match essentially the resonance of the alpha particle plus the beryllium 8. And that is how the triple alpha was really kind of understood, theoretically first, and then the Fred person postulated that there's going to be a resonance state. The nuclear experiments went to look for it. And the initial motivation to prove it wrong. How arrogant the theorists could be, telling us that you miss the resonance state how it works, right? So they find it, and so that's how we understand how this is how we really believe that in stuff solved.
Yeah, another video you show
Yeah, it's the same thing. It's the same thing. Yeah, it's the same type of process. As I say that again, when you have in a neutron environment, so the proton has been rounded up with equal number of neutrons in helium-4, then you only left with the neutrons in helium-4. You say, if I only go by two-body reaction, what I can do? The helium plus neutron, helium-5 doesn't exist. Then you say helium-4 plus helium-4, that's the only way you can possibly do it. And that is essentially just a beryllium again. The beryllium now has an initio type because it's neutron. You don't require an alpha particle. You can just bind with the neutrons. And that allows you to make beryllium 9. Again, it's a resonance state. You can build up your beryllium 9, go back to alpha, and the binding rate is also not very high. It's like about 1.78 years. So the temperature is high enough that the beryllium 9 will be very low abundance. But at least it's stable. It's a stable nuclear. So this kind of abundance is much easier to be acquired compared with the triple alpha. So that's the reason why you can make a lot more seed nuclei in this environment compared with the Big Bang. Remember, in the Big Bang, you got proton rich, and you combine equal number of neutrons and proton, they get helium-4. You left with proton and helium-4. And helium, lithium-5 doesn't exist. And you say, how about the helium plus helium? you can do that, you end up with a very 8, and you say that not only can it have something to do with the triple alpha, but the temperature is very low. You cannot possibly have a resonant reaction proficiently going on in the universe to make carbon. That's the reason why the universe started with helium-4 and proton. They didn't go beyond carbon and things like that. Whereas in this neutron environment, it's entirely different. Because with neutron, life is a lot easier. You make it very high, and it's a stepping stone for you to go to carbon globe, and the rest of it is purely by the body reactions. And this is the reason why we can basically see things like the because of the stepping. If you kill off the line, it doesn't state. It's just not going to be very easy to make a thing. But you still going to be making some of these very different stuff. Some abundance will be very low.
So in this our process, it occurs far away from this definition. And in my understanding that most of the network calculations just taking the masses and calculated by the theoretical models and good. So I'm just curious, in this triplet region, they also have many exotic structures where this impact this abundance of the matches elements.
It's a very good question. Obviously, the way I'm thinking here is obviously mostly like an overall picture. The details, obviously, the devil's always in the details, right? So, for example, the two peaks, they are tied to the closed neutron shell structure. That's qualitatively true, right? But exactly the height of the peaks is very complicated because it really depends on a lot of details. For example, as I said, this is essentially the stable nuclei you mentioned on May. This is essentially the region of operation, between here and here for our process. And most of the information regarding nuclear masses and regarding neutron empty perceptions and regarding beta physics are unknown. And so we are mostly groping in the dark, filling in the details with some theoretical estimates. I wouldn't trust many of these things beyond especially the periods that neutron capture rates beyond and all the magnitude estimates. The masses are better because they are now getting to be measured in these astronomical radio isotopic facilities. I think the masses will be measured better, but the way to now calculate the neutron capture cross-section plus the beta decay rates and also the fission rate. Those are much more theoretically considered. And so I think we perhaps will never be able to really artificially predict explicitly this gotta be the abundance curve produced by this environment exactly. It's perhaps never going to happen. But what we will be able to do is to say that with this kind of initial conditions, roughly what range of nuclei we will be able to make. And roughly what will be the shape of this infinity line. But not in this very detailed way to say that I can be exactly to predict this one. And it's also very hard to measure them observationally. Say what is a particular end product of an R process. Because if you do spectroscopy speaking, you use the telescope, look at a line, and then you measure different lines, the strength, and to find out what's relevant balance in there. And there you talk about the logarithmically, the balance is like 0.3 deck. That's a factor of 2. So it's very hard to nail down either one. But I think that from a semi-quantitative point of view, that's not an issue. And if we wanted to just prove that, say, it's this group of nuclei made by the R process must happen in this event, that we can probably do. And that's as we have seen it in the neutron convergence with observed in 2008. It's 2008, 1708, 17. Basically, that's even we have seen. And the reason is also very interesting. That's a lot of interesting atomic physics. So first of all, when you have beta nuclei, initially they are very neutron rich, and they beta decay. And as they beta decay, they obviously would sometimes decay to excited states. Again, likewise, they're going to emit gamma rays to these sites. And all those gamma rays eventually will be thermalized because the initial material can be very thick and they cannot escape. Just like the supernova light curve, they will be glowing in some kind of optical light proposal rays. But the interesting thing here is that when the photons can escape from the thick environment, depending on the opacity, that means the cross-section of the photons are incorporated the atoms made from these neutrons. And if you look at the theoretical table, there are two special rows of elements. One is called the lambda lines, the other one is called actin lines. They are special because they are the ones that each shell of the electrons start being filled. And normally you think about SPD, F, these shells like that. Those are the shells that mostly don't use up in doing most of the elements up to fineness. Starting with lanthanum and actinides, these are the shells which will be started filled. And when you have an entirely new possibility for you to make atomic transitions, that means the photon has a lot more ways to talk to this particular atom. That means the cross-section goes order of magnitude high. That means the photons cannot escape easily. You have to wait for the environment to basically thin out further. The density goes lower, the temperature is going to be cooler down. And so the color, you're going to emit, if it's a semi-black body thing, then the color will be more towards the red, more like inverse. And this is how the so-called red killer was found, a company that becomes familiar with. If you make iron type of stuff, or even strontium type of stuff, below the lanthanum, you never get that color. And because you see that color, we know it is at least a lanthanum material. So qualitatively, we know that's what's happening. But in the details about the manuscript, perhaps we never will be able to achieve. But that doesn't stop us from trying. We can always get it as close as possible. Maybe 10% level effectiveness will never be achieved. How about factor 2? If we can do that, that's still progress. Fine.
有再加上3页之前的非常有一个人说，
线上的老师同学有没有问可以直接提问。
基本上
那我也
没有。
发现直播，
非常不一样。然后我们这边肯定有所以是更加
去的那个
一那个影片很少，影片很难的说，如果是都是他说，就因为这个有每个 branches， 因为拿了还是他就reach about the 5 months and sometimes 一些sorry 的。For those things that you want to do, essentially what you do next to that is so this again, basically we know that how do I say? I also should say that so I think happens for maybe as starts at higher temperature, whereas for those is a lower temperature. Part of the reason is because at the same that's the high temperature. That's why there are the high temperature again. But this one over here, because as you think about the atom story, the temperature is very large because you know the yes, the initial temperature that's so high, you can reach a higher temperature because you have a much of a mass. And when the temperature is high, you can also more special. contributing from photons to radiation pressure. What I'm showing here is just a regular positive. But eventually, the temperature is high enough to convert the radiation. Radiation going to the form. And so the structure is. So the lower mass will be dominated by the reactants of the inverse. The high mass will be dominated by the radiation. I should have done that post-order. Because that's the shape of it.
年轻人没有问题吗？不懂是吧？还有没有什么问题？如果没有什么问题，那么我们再次感谢他。
If anybody wants to